This problem is from the book, has to do with a spring and a mass attached to that spring. K is the constant for the spring. M is the mass. And the motion is governed by this sinusoidal wave, in this case the sine curve. So in the first part of A, they want to know at what times is the mass farthest away from equilibrium. So that would be here, here, and here. So that looks like that's when the velocity is 0. So we'll take the first derivative, which is the velocity of the mass, and set it equal to 0 here. And that works out like this, because the A is a constant, and so is the square root. That's a constant. That divides over, equals 0. So we're looking at what angles make the cosine 0, and those are 2n plus 1, pi over 2, odd multiples of pi over 2. Divide over to solve for t, and you get this expression. And so those are the times where the mass is farthest away from the equilibrium, either positive or negative way. In particular, for n equals 0, because they just asked for one value. If n equals 0, then t could be equal to pi over 2 square root of m over k. Then the second part of that question, when is the mass moving the fastest? Well, that's when the velocity is maximized. So we'll take the second derivative, which is the derivative of the first derivative, and work it on down here and set that equal to 0. Come to here. Then we're going to go to the next page, and you have your equation equal to 0. Again, the constants divide out, and you're looking for the angle that makes the sine equal to 0, which is multiples of pi for n equals 0, 1, 2. It would normally be negative values also, but it's positive or 0 in this case because time is starting at 0 and moving forward in a positive direction. So you simplify that out and solve for t, and you get this. And in particular, they just ask for one time, and where the velocity is maximum, and that's at n equals 0. Is the simplest time. T would be 0 then. For the third part of the question, when is it accelerating the fastest? Then you would have fastest y double prime maximized. So you take y triple prime, which is a derivative of the second derivative, and work that out, set that equal to 0, and that solves out here. Again, they just want one moment when it is. So if n equals 0, then t equals pi over 2 square root of m over k is one of the values, one time when the object is accelerating the fastest. Then they ask another question, part B. What is the period of this motion? That's 2 pi over the coefficient of the t inside this angle, which is going to be simplified out to this. And I wrote it with the 1/2 power because in part C they asked for the derivative of the period with respect to the mass. So how is the period changing as the mass changes? So you take the derivative of the period with respect to m, so the 1/2 comes down the front, decrease the exponent by 1, gives you the negative 1/2. Simplify that a bit, and that's the way the answer looks in the book. Then they want to know what sign is it and what does that mean. Positive, negative sign, it's always greater than 0 because the pi is a positive number, of course, and so is m and k. K is a spring constant, it's positive. M is a mass, positive. Square root, of course, is positive. So it's positive, which means that the period as a function of the mass is increasing. It's an increasing function, which means as the mass increases, the period increases. So bigger mass, you get a bigger time for the object to complete one of its periods, one of its motions to return back to 0. But also notice that the derivative of the period with respect to the mass is pi over square root of mk. So that means as m increases and gets greater, yes, the period does increase, but the rate of change of the period decreases. It gets less because m is in the denominator, which means that if you increase the mass, you are going to go up with your period, but you're going to go up by less and less and less as your mass increases.